Time for another adventure in Lewis structures and resonance structures and which structure is best type thing. And this one comes out of problem 8.107 out of the Brown and LeMay text. And it's actually kind of an interesting one. One of the, late in the end of chapter questions where they get kind of a little funky with their problems and stuff. And this one involves phosphorus. And they tell you that phosphorus exists as the one common way that it exists is the P4 molecule. And they even draw you a nice pretty picture of the problem, or of the molecule. And so let's take a look at the overall question, which includes the pretty picture here, as we often do, and then we'll start tackling the individual parts of this thing. So here it is. Now the P4 molecule, they have that pretty picture where each phosphorus is on the corners of a tetrahedron, and they ask us a couple of questions about it. Part A, do the phosphorus atoms in P4 have any lone pairs? And in part B, how many phosphorus-phosphorus bonds are there in that particular structure? Now, I'm going to redraw it here a little bit and go through the process of coming up with its Lewis structure. It's not going to be nearly as pretty as the graphics they put in there, but oh well, we'll work with it. And this one is kind of an interesting one because it's an example of drawing a Lewis structure. We're going to follow all 6 steps that we usually do, but it's going to be a little bit different than some we come up with. So with this one, with phosphorus, there's not one, the way they kind of phrase it, there is not one single phosphorus in the center here. The phosphorus atoms in this particular molecule are at the corners of a tetrahedron. So all I'm going to do is just kind of draw the 4 phosphorus kind of like this. You notice I did not put one phosphorus in the center and put the others around it, which is what we would normally do in most molecules. For this one, I just kind of wrote them up here, kind of 4 phosphorus around a little bit. But now we are going to go through the process of drawing its Lewis structure using all the standard rules that we've come to know and love. Step 1 is identify the central atom, and they've kind of come out and told us and even drawn us a picture that this one does not have a central atom. It's kind of this cluster of 4 atoms here. So part 2, total number of valence electrons. Phosphorus, of course, is a member of column 5, and there are 4 of them, so we have 20 valence electrons to put into this thing. Absolutely no more and no less. Next step, put a pair of these electrons between each of the phosphorus atoms, and that's exactly what I'm going to do. I've used 1, 2, 3, 4, 5, 6, notice 7, 8, 9, 10, and even 11, 12. Okay? And so I've put a pair of my valence electrons between each phosphorus atom, and you'll notice essentially each phosphorus now has 3 bonds on it, is sharing 3 electrons with its other friends in this particular molecule. So I've used up 12. I have 8 left. Okay. Step 5, my outer atoms. Well, I'll use this one as I don't have a central atom in here, but so these are my outer atoms, and I'm looking for the magic electron configuration. Do they have the octet? And each phosphorus has 1, 2, 3, 4, 5, 6 electrons, 3 bonds, 6 electrons total at the moment. So each of them needs 2 more. 1, 2, 3, 4, 5, 6, 7, 8. I happen to have 8. I have used all 8. I am out of valence electrons. Now, step 6 says worry about the central atom. I'm going to basically say, let's make sure everybody in this structure has a magic electron configuration. And they do. This phosphorus right here, 1, 2, 3, 4, 5, 6, 7, 8. This phosphorus, 1, 2, 3, 4, 5, 6, 7, 8. And the same for the other 2. We have every single phosphorus in here having a magic electron configuration, no violations of the octet rule. And so there's the structure, and we can answer parts A and B pretty quickly about this in this problem. Part A asks us, do the phosphorus atoms in this particular structure have lone pairs? Yep, they do. Okay, I was going to say yep, but we'll make it formal. Yes, they do. Then part B, how many phosphorus-phosphorus bonds are there? If you look at it carefully, you'll see there's 1, 2, 3, 4, 5, 6. Okay, and this one I have kind of broken because it's passing behind this one. So there are a total of 6 phosphorus-phosphorus bonds in this structure. Okay, so parts A and B, drawing the Lewis structure is a little bit odd, but that was pretty simple. And then parts C and D, they ask us, okay, consider what if this molecule were actually linear? What if it was just a line of 4 phosphorus atoms? Can you draw a Lewis structure that doesn't violate the octet rule, doesn't have resonance structures, and compare those structures with this particular one? So slide over here just a little bit, and I'm going to say, okay, let's try to draw this thing. I'm going to put 4 phosphorus atoms out here in a line, okay, because that's what they're talking about, to draw a linear structure. And it still has its 20 valence electrons. So following the rules once again, I'm going to put a pair between each. 1, 2, 3, 4, 5, 6. And let me make a list of my 20 valence electrons again. I have 1, 2, 3, 4, 5, 6. So I have 14 to go. Worry about the outer atoms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are the outer atoms now. I have used all of my valence electrons but 2, okay, put 12 in here, so now I have 2 left. So now I turn my attention to the central atoms, making sure they have their magic configuration, and I have to stop, okay? I want to put more dots in, but I have to stop because I'm out of valence electrons. So here is the classic case where I've run out of valence electrons, and so the answer is to start forming double bonds and or triple bonds. How do you get everybody with a magic configuration using no more electrons than 20? Okay, and one of the ways to do it would be to get these two working well by sharing one of these pairs of electrons. That gets me this phosphorus with a double bond. Okay, that gets these two with a nice octet. Everybody has their 8 electrons. Now over here, I'm going to have to share 2 extra pairs here, leaving this phosphorus, take that pair here, take this pair in there. That gets me a triple bond over here, but it does give every single one of the phosphorus atoms in this particular structure the magic electron configuration. It has the octet. Okay. Now, when you talk about resonance structures, you're basically asking, are there any other ways to draw this combination of singles, doubles, triples, and stuff that would give magic electron configurations to everybody, not violate any of the normal, octet rule type stuff, but a possible different arrangement. And there is one other one that you can come up with fairly readily, and that is to put double bonds between everybody. Okay, that would come up with this type of structure, where that lone pair is going to go here, give me a double bond there. Now, that means I have to put one of these lone pairs back over here on the phosphorus, and that would be the other alternative structure. Put a little set of resonance arrows between them. Okay. And so these are the 2 structures. Now, yes, I could redraw this one again with a triple bond on the left, a double bond on the right, but that just repeats this one here. And I think these are probably the 2 most reasonable ones, or the 2 that you come up with, the 2 that you should come up with. And so here are the resonance structures for linear phosphorus. Again, there's our fabulous little tetrahedral structure. And question C, and make sure I get it, yeah, question C, draw the Lewis structure of the linear. Are there resonance structures? Yes, there are. And then question D, okay, which one is best? Is it this tetrahedral structure or this linear type structure? And of course, that is a formal charge question, okay, where you have to go through and calculate the formal charges of these. And what you're looking for is, do you find a structure that minimizes formal charges and puts the negative formal charges on the most electronegative atom? Since the only atom in any of these structures is phosphorus, that really isn't a consideration for this particular problem, but we are looking for minimal formal charges. And so we remember the little formula here, that formal charge, okay, there's a lot of ways you could express it, but the way that I tended to learn it was number of valence electrons minus, and then in parentheses, the sum of the number of non-bonded electrons plus half the number of bonded electrons. And I just abbreviate a little NB and B just to keep it simple looking. Okay? And so I'm going to go through and do a couple of these. There's no need for me to, laboriously, record myself putting the formal charges on all of these. There's a lot of them that are going to repeat. But I am going to go ahead and do this one and then do one of these over here. So for this particular phosphorus down here, it's a phosphorus, and so the number of valence electrons is 5. Okay, that's going to be pretty standard for all of these. 5 valence electrons minus the sum of the non-bonded electrons in here, 1, 2, 3, 4, plus half the number of bonded electrons. There are 2 bonds here, each containing 2 electrons, 1, 2, 3, 4, and so half of that. And so what I end up with here is 5 minus 4 plus 2. 4 plus 2 is 6. 5 minus 6 is negative 1. So the formal charge on this dude is negative 1. Okay? And if I go through and repeat that, I would end up with a negative 1 here. And these, for these two, the formal charge calculation comes out positive 1 and positive 1. Okay? So there's that one. Okay? This one, repeat it. It's actually just a repeat of this one, negative 1. Okay? Come over to this one. This one actually has a formal charge of 0. Okay? This one will have a formal charge of 0. And this one will have a formal charge of plus 1. Okay? And I just use the same formula for all of these. Now I'm going to come over here, and I will write this one out in detail for this one. And again, these 4 phosphorus are all identical to each other, so what I do for one, I've done for all of them. So for any one of these phosphorus, I'll use this one because there's some room around it. The formal charge is the number of valence electrons, 5, minus the number of non-bonded electrons, 2, plus half the number of bonded electrons for this. And we've got 3 bonds, so 1, 2, 3, 4, 5, 6 total bonded electrons, okay? Which becomes 5 minus 2 plus half of 6 is 3, 2 plus 3 is 5, 5 minus 5 equals 0. So each atom in this particular molecule has a formal charge of 0. And there it is. It becomes pretty obvious what the answer to part D is. Which one is the best structure, the tetrahedral structure, or one of the linear structures, depending upon which resonance structure you like. If the choice were between these two, you would go with this one because this one has, formal charges, more formal charges that are 0 than this one does. But these two are wiped out by the fact that this structure here has only 0 formal charges. And of course the criteria is whatever structure has the smallest formal charges is the best structure. Boop, that's going to be the tetrahedral. And so there's that particular problem. Technically, I think the challenge is this is a little bit more of an elaborate structure than, like drawing water, one central atom and a few outer atoms here, but the rules still apply. All of this calculational type stuff for resonance structures and which one's best still apply. So it's not a terrible one. And so take a look at that, look it over, and make sure you can do this or stuff like it on your own, and we'll talk to you later.